Okay, so with the benefit of some sleep, the problem becomes completely obvious. Right, so we're really struggling with this notion of when we come here. I've temporarily broken this, so in fact, actually, I don't know if I've broken it because of the trig or whether I've broken it because I just made them white and the background is white. Let's just have a quick look. Okay, there's something drawn up here, so yeah, so it looks like I've broken the trig. Right, okay, so let's think this through. So our R values based on the system that we're generating are between 0, where gateway is, and 150. So R varies. R is going to be somewhere, let's do it this way, from 0 to 150. Okay, sine theta is going to vary from -1 to 1. Cos theta is going to vary from -1 to 1. Our box is 0, 0 in the left-hand corner, 800, 800 in the bottom right corner. I wish I could stop doing that. Where was I writing? So, and our problem was once R went over a certain value, we started plotting outside the bounding circle. Well, of course, the answer here is to recognise that we're getting this from -1 to 1. So when R is at max R, we want to be on the bounding box. So clearly what we need to do is do a unit vector conversion here. So R over max R gives us 0 to 1. Now R, so this is scaled R, right? So scaled R is also going to give us this range. Okay, but we need to translate the extremes of this range into this range, so we need a scale factor. So in fact, we add 1 because we want to normalize it, which will give us 0 to 2, and then we want to multiply by 400 because 2 should be 800, which is what we're doing now. So we have our max R, so max range is 150, which we do here. So scaled R is R over this dot max R, so that's going to reduce R to the unit vector. Now we take our random angle, and so we do scaled R math cos theta plus 1, so we're turning the range -1 to 1 into the range 0 to 2, and then we multiply by our scale factor, which is related to this. We could actually calculate this scale factor. We could do this as return this dot map width divided by we got a scale factor of 2. I think that's how we ended up with this. Where was it? This stuff down here. But we can now eliminate that. We don't need that anymore. Map R. I don't quite. Where was map R used? So it's used in here. Right. So this should actually be max R. But when you draw circles here, we're drawing them in pixels. So this is not quite right. That's going to need to be fixed because, yeah, we need to convert that Right, that's foxed me for a second. So this is the bounding circle. So within here we draw a circle. I think the reason I got confused earlier is this has now gone nuts. If we make this 100, we'll see. Okay, yeah. So yeah, I did want to do this as white because that should be black. So let's just go back and change this to white. Okay, so so the issue here is to draw this bounding circle. We need to apply the scale factor. Now, by inspection, it looks to be about 3. Maybe it's 2. Oh, so by inspection, it's 2. So R400. Well, that would make sense because this is an 800 by 800 box. So a radius of half of that would work. So map R, wherever that's gone, return this dot map width divide 2, and we can now do this back. We can now put this back to sector dot map R. Well, let's call this bounding R. I think that's probably slightly better. So that's not really related to anything. It's just okay. So now we defined our box here, but the question is now these are not being drawn properly. So we have map X, map Y. So map X and map Y are wrong. But in fact, actually, I think we can just now I've fixed that, I think we can just do system.x, system.y. Yeah, there we go. Okay, so that looks more promising. I would have expected something a bit further out. I don't really like how this is being generated, so I'm just, for every system I'm generating a random angle, and I think it doesn't, I don't know, let's have a look at a couple more. I mean, the main factor is it works, right? So we're now, I mean, I guess we can't see. Okay, I think what we can do is can we set the can we do that? It's not fill, is it? It's background. Is it background color? Yeah, okay, right, so now we can look and see, are there any white circles outside of here? There is a white circle up here, actually. What circle is that one? Can I inspect that? This is gateway, which is at yes, okay, right. Gateway is a special case. Yeah, gateway is a special case because we've set X and Y here, but in fact that's not right. Yes, these are now, right, I remember why I had X and Y now. These were designed to allow us to calculate the distance between systems. Yes. So in fact, actually, this becomes right. Yeah. Okay. So we don't want random colours anymore. That was just so we could see them apart. We know we can plot now, so we can just leave this as white for now. Eventually, what we're going to do is plot it based on the star colour. But let's not get too thing with that at the moment. So we've now got this. So map CX, the sector map we draw relative to. We do use that, don't we? Do we? Yeah, map CX, map CY, although it's really kind of trivial. But we'll leave those as they are for now. We've got a scale factor of 400, which so we can lose that. This coordinate range thing ceases to be a thing. Bounding R is here. No, we'll put it here. Okay, if we could do expressions in here, I mean, I could actually do this with JavaScript, I guess. No, that's not really the problem right now. So let's stay focused on. Yeah, so actually, what we're going to do. So system.x is going to be scaled R times math.cos theta. Do I want to keep the offset adjustment in there, +1? So that would be 0 to 2. So we translate the native -1 to +1 into 0 to 2. Okay, let's leave this unadjusted for the moment. And system.y is scaled R times math.sin theta. Okay, so right. So we introduce system dot where are we? So we've got x and y. What we're going to have is mx and my. So this is the sector x position. This is going to be from -1 to +1. This is the sector y position from -1 to +1. This is the sector radius from gateway from 0 to 1. Okay, this is the map x based on sector x, and this is map y based on sector y. Okay, right, so we're going to keep this position because that allows us to calculate hyperspace distances. And now what we're going to have is system mx equals system of x plus 1. So we normalize to 0 to 2 times this dot scale factor. And system.my is system.y plus 1 times the scale factor. Okay, right. Now, we don't need to do that. System.r equals, yeah. So we can hear here system.r equals this. So system.r equals scaled r. Okay. Right, yes, boom, okay. Right, so we generate the system. Okay. That's better, right. Okay, so Okay, what we're going to do, we could cache this later if it turns out doing this calculation hundreds of times is a performance issue. But if we do this, we can get access to the scale factor from the system itself. So when we create the system, system.sector is this. Create system name XY. So comes system SY templates. Right, so the issues about gateway, I think actually now, so we've got the defaults for the star system. I think now actually that should work if we use, system ID is sector, was it? Sector. So we implicitly put this into the sector, although the sector won't know about it until we add it later, which we do here. We know sector exists, so that's okay to do. And if we now plot this with sector dot map x and map y, that should still work. Okay, it breaks. This dot sector dot scale factor is not. What is this? This is gateway system. Oh, its sector ID is not set. We do that here. Where are we when we're doing this? Well, we're in the renderer, so everything should have been set. Gateway system. Right, so we're trying to draw gateway and gateway's failing. Ah, yeah. Sector ID. Stupid. Okay, I should fix that. Boom. Okay, right. So we're now plotting using map X and map Y from the system. So we no longer need to do that stuff. We don't need to set MX. We don't need to set MY. So we just set the R value, X and Y, and then we let it go. We don't need to do anything else at this point because now gateway is actually being plotted properly in the middle. Now what this would mean now, because we've now fixed the scaling factor, if I now set this to like 200, this would work. If we set it to 500, this will work. So we could set this to 151 to ensure that nothing ever draws directly on on the circle. I'm not sure if that would actually work because these are radius 3, so it's possible they might still overlap with the edge. But I think we're sort of at the good enough point with this now. Let's get rid of that background colour because we now know that we're not plotting outside the circle. So in fact, this was incredibly simple to fix, and just my really not looking and thinking properly. So we now have the sector plotting properly, and we've added some outer rim systems, and the distance here is considerably greater. What we might do, because I'm now sort of thinking to myself, okay, that's cool. I don't know how well this will work, but I'm going to set this to 201. And then what we're going to do is we're going to plot these at 150, at 175 to 200. Now what that's going to do is that's going to compress the main system, but now you see we've got these outlier systems that are considerably further away. It had an unfortunate squashing effect on the main sort of centre of the sector, but now you can see here we do slightly overlap there. I could probably fix that if I'm careful enough. But what you see now is if we were starting at gateway here in the centre here, these systems are now quite a long way away. That's had a slightly unfortunate effect on the map, and maybe we don't need to go quite so extreme as 200. So what if we said 175? So we were at 150, we're now saying 175. So this is now 175, and let's say this is 165. And let's just look and see what that does. Okay, that's a bit better. Still got a nice big gap. Let's go down to 160, and this now becomes 155 to 160, because we don't want to squash too much. Okay, that's not bad. That's not bad. But let's try going back even more. So originally we were 150. Let's make this 155. So these go to 100. Actually, originally, yes, the outer systems are 100. Right. Okay. So if we were to go 120 even, so the outer systems go to 100. So here, let's say we do 110 to 120. Let's have a look at that. Okay, now that's not bad. That's not bad. So now let's go to 125. Okay, this I like. So there's just this little bit of extra distance, this little extra gap here. There's so few systems we don't actually, yeah, I quite like that. So we've got this dot of systems around the outer rim that are just a little bit further away from the core. Yeah, I'm not unhappy with that at the moment. I could tinker with this. The gap's been compressed a little bit. So what if we go to 130? And we do these as 125 to 130. Yeah, so we've got these little clusters of systems that are just that bit further away, just that bit harder to reach. You've got a limited number of ships to play with. Sending a ship this far out, that is going to be quite a dramatic. I mean, it's going to take the ship out of service for a long time to get here. If we think of hyperspace travel between systems. you've got situations going on in these kind of core and inner systems. Sending a ship out to explore this system, that's going to be quite, that's going to take it quite a long time, where it's out of service, so you really got to want to explore these systems. Maybe getting here is problematic. In Star Sector, hyperspace has stuff that means it's not a linear map. You have nebulas and storms and things like that. I'm not sure I want to do that. But just the act of sending a ship that far, which is like from here to here, and then compare that from here to here, it's a much further distance. It's going to take longer. We'll have to see how it plays out in practice. Maybe in practice it turns out it's not very long, and this, okay, it's 5, 6, 8, 10 times, but it's still not all that long. But I'm not unhappy now with how that's being plotted. We've got these systems on the outside edge, so that's pretty good. So my next thing to focus on is going to be stars, I think. So I have this spectral class table. We're going to, for the moment, we're just going to focus on single stars. In fact, multi-star systems are pretty common. I got this table. I used GPT to tell me about star distribution. So this table is, it may not be accurate, but I did look at some of the references and where I thought binary or trinary systems would be really kind of rare. It turns out they're really not. In fact, they're very common. But we've got this spectral class table, and I'm not an astronomer, so so we've got O, B, A, F, G, K, and M. O, B, F, G, O, B, F, G, A, K, and M. Right, so we've got our stars. Let's have a look at this table. Okay, so we've got colours. Okay, so this is kind of interesting stuff. So we get a colour from these. I don't really know what this is doing. Size solar R. What kind of star? G2 main sequence yellow dwarf star. So G here. 2 is goodness me, the sun is old. It's going to turn to a white dwarf. Magnitude. Okay. There's helium, the hydrogen here. So hydrogen 91%. We're a G star, hydrogen weak. I don't know if that relates to this ratio between hydrogen and helium. We also seem to have L, T, and Y here, which aren't in this table. But this does say it's a simple table. Modern classification, Morgan scale. Okay. Right, so I don't know what chromaticity means. That's Okay, so we have this class scale. Okay, I think this is probably where my table here comes from. Where's it gone? Oh, here. I think I've calculated some relative probabilities here. So we say if 0.03 is 1, so O has 1. This is 3,250 times more common. So I'm pretty sure that's where I got that from. So if we go in here and we pull open, I never remember the thing for this. So sector.systems. So we've got these systems here, but these are IDs. I think sorted systems actually gives us the thing here. In fact, we could just do sector system dot. What is it? It's not refs. Is it refs? Yeah. Okay. Dot. That gives us a system. Spectral class M. So if we were to map over those, so sector dot systems dot refs dot map, we get a system, and we ask for its spectral class. With this number of systems, you can see that they are almost all M with a smattering of K's and G's. We did get a B. Oh, there's actually a relatively large number of K's. Okay, yeah. If we've got a B, do we get an O? Are there any O's? Actually, what we can do here. Okay, right. So in that number of systems, we've got some M's, K's, G's, and F. Where did our B go? Was that from a previous version? I think that might have been a previous. No? No, we've got a B here. What's going on? Where did our B go? Ah, yes. Right. This is a probability table. So in fact, actually, if we do SY gateway, in fact, we'll get a different one every time because it's not actually assigned. This is a sampler. So if we were to do this. Is it not number times? Oh, it's of, isn't it? No. Shit. What is it? I've got a function here somewhere. Or is it math? Oh, I don't know. It's probably math, isn't it? It probably doesn't belong in math. But math is sort of... Oh, actually, hold on. Where is it? No, it's array. It's array of. That's what I thought it was of. Array of. Here we go. So n of 1,000. Okay. And then we say frequencies. Okay, why didn't that work? because I need to make this a function, otherwise it just samples that version once. So we do that. There we go. Right, okay, so we've got lots of M's, a few K's, some G's, a small number of F's, and A, no B's. Let's have another look. Okay, again, let's generate 10,000. I think the thing is the frequencies are accurate. Work because there are millions and millions of stars. Okay, so now we start to get a couple of B's, but we don't have any O's, and I think the way this frequency table is set up, so if we say let's do 1 million of them, even with 1 million we still didn't get an O. Let's do 10 million. We're going to start to strain the browser, I think, if we do that. Okay. With 10 million stars, we only got 3 O's, which is statistically accurate, but not very useful. Now, either we don't need O-class stars. These are blue stars, very hot. We're going to need to change this. If we want to see any of these, we're going to have to change this, because this is accurate, but we're not in the realm of accuracy, because if we were accurate, we'd be doing 10 million stars, whereas actually what we're doing is something like 200 stars. So this is an accurate table, but it turns out accuracy is not super useful to us here. So this is accurate spectral class. Let's do another table. So this is a Rez feature which is useful for procedural generation, which is a probability table. So if I do this, and I do this, you'll see we get A, B, C, and D. So Rez keywords turn into strings in Java. And you can see that these are, statistically speaking, pretty much the same. But if I change B to 2 now, and do the same thing, what we'll notice is that B is now considerably higher. It's about twice as high. And what this is relative frequency. So by setting B to 2 here, we say the relative frequency of B is twice as often as the other options here. If I set D to 4, and just, we don't need quite as many samples here, so let's just do 1 million. What we can see is D is now about twice as common as B, which is twice as common as A and C. So this probability sampler, now we can do actual probabilities here, so we could do 20, we could do 50, 20. So you can do a probability table with strict probabilities if you want to, but you're not constrained to that. It works for that, but you're not constrained to that. So each time you look at spectral class, it will sample this table and give you one of these 4 outputs based on the relative frequency of those outputs. So that's what this function feature does. So if we say O is 1, B stars are much more common, but let's take the square root of these numbers as a starting point. So what's the square root of 3,250? Is 57. So let's make B 57. And the square root of 20,000 is what? like, actually I don't know. Okay, it's not what I was going for. So we've got 141. So A stars 141. The square root of 10,000, that is 1,000, right? Yeah, 100. 100 squared, 10,000. Ah, but it's 20,000. No, this is that's 100,000. Sorry. It's 10,000. No, it's not 316. Okay, completely wrong. So F stars. What have we got here? 316. G stars. That's 233,000. 333. I'm not even going to guess now. Completely out. So 483. K stars. So that's 400,000. Square root of that is 632. And M stars, let's just grab this, so the square root of this is 1602. Okay, so I've damped down those probabilities, and we could do that again, but let's see what that looks like. So we go back to sampling the frequencies here, and here with 10 million we're getting a decent number of O stars. So let's go back to generating the sort of numbers that let's say 1,000 stars. So if we have 1,000 stars, how many O stars do we get? None. Do it a couple of times. Right, so 1,000 stars, our probability of getting an O star is still, one more time, let's see if we fluke an O star. Yeah, okay, so we fluked an O star, so in 1, 2, 3, 4 runs, we got 1 O star. So that's probably still a little bit too, I mean, they are supposed to be rare, but let's say we'd like to make sure that every sector's got a chance of getting at least 1. So what we could do, instead of doing the square root, is we could try the cube root. So the cube root of 3250 is 14, call that 15. So let's keep this, let's duplicate this, because that was our starting point. So this is 15, the cube root of 20,000 is, call it 27. So 15, A goes to, which one did I do? Oh, God. Right. So I did 57 went to 15, right? No. Right, that's right. So I've already. It's these I'm doing. Right. Keep up. Right, it's 15, 20,000. So this is the A stars. 20,000 is, call it 27. So this is A stars. 27 F stars is 46, so F is 46, G is 62, so G is 62, K it's got 74, K 74, and we've got 137. Okay, so we scaled down again. And what we're really interested in is O. What am I doing wrong? That doesn't really make any difference, right? Frequency's got, oh, it's a map. I forgot it's a map. Yes, frequencies gives you a map. So get, yeah, here we go. Right, so get O. Okay, right, so we run it. Okay, so on this basis, we now, with 1,000 stars, we seem to be pretty much guaranteed to get one. Obviously, there's a chance that we wouldn't get any, but very unlikely chance. Okay. Oh, I switched to I was thinking, well, what did I do? Okay, so, right. Okay, so good. It's pretty right. You see here, we didn't get one. We didn't get one there. We didn't get one there. So in fact, actually, we can do this. Get. So let's make this get O. Bit like that. Let's go back to this. So that says get O. Okay, right, so you can see if we generated this system 10,000 times, so what I'm doing here is, so this is sampling the frequencies of 1,000 stars for the number of O stars. So it returns undefined when there are no O stars. So we turn that into a function that basically says, do we get at least one O star? So f now is f is a function that says, if we generate 1,000 stars, true or false, we got an O star. So then we run this system 1,000 times. So running this here, so we're running this system 10,000 times. So in 10,000 times generating 1,000 stars, 642 times, which is what about the relative frequency of that. So 642 over 9358. Yeah, so it's about 7%. About 7% of the time we don't get an O star. I'm not sure how important it is that we do actually get O stars. We could tinker with this again. So let's divide this by 2. So that becomes 8. That becomes 14. That becomes 23. That becomes 31. 37. And that's 60. Well, let's call it 68. Okay. Right, so let's redefine this. Okay, and then we'll run it. Okay, so now out of 10,000 runs, only 40 times we don't get an O series star. That's actually still quite high. I mean, obviously it's a very low percentage, but it's not a 0%. Does it matter if we don't get an O star? Probably not. It probably doesn't matter. Okay, something weird's going on with my mouse. What the hell's going on here? That's very puzzling. I wonder if it's something to do with the browser. I've been generating a lot of objects here. Throw in the garbage collector or something. Okay, it seems to have settled down. I mean, this is the problem with any system based on probability, is you can get outliers. So if you played this game 10,000 times, 40 of those times you wouldn't get an O class star. I guess that perhaps doesn't matter. So I think what we're going to do is we're going to go with this table. We're going to go with this table for the moment. So each of our stars when we generate them, but we want gateway to be a perfect star. So okay, so gateway, what did we say Sol was? Sol is a G2. So G here, yellow star. Right, okay, G2, I think 2 is like the luminosity, although 2 wouldn't be work. Maybe that's a class rather than an actual luminosity. So it could, I don't, where did I get that from? I think I got that from, so my friend Chris Bateman back in the 90s published a game called Outlands, which was a space game. And Chris being Chris, it has a, at least for the 90s, an accurate system for generating stars. So we want it to be a G star. So it's going to be an Earth-like star. So Gateway turns out to be interesting because Gateway has Gateway has spectral class G. But our other systems, okay, right, let's see, does that work? That fails. If we spell spectral properly, that would probably solve the problem. Okay, so SY gateway, spectral class, we can already see it's G. Okay, fine. But if we look at the other systems, so we go sector.systems, refs, map from system to its spectral class, and you can see we've got a whole bunch of spectral classes, so that's been assigned properly. Frequencies is such a useful method. I mean, Clojure has frequencies. That's really where it. I realise just how useful it is when you have that on tap, particularly for these kind of things where you're generating stuff dynamically. Being able to just sample and go, okay, that's the distribution as it works. So you see in this example, we don't have an O-class star, but we are only generating about 200 stars. So it's perhaps unsurprising that we don't have an O. We have a couple of B-class stars. We can come back and tinker with this later if it turns out to be interesting. My reason for doing this principally is because I don't know how much play the star is actually going to have in this. It may be about whether there are Earth-type planets that could be settled. And you see here we've got 21 kind of G-class stars where I'm not an astronomer. I don't know really very much about this. So we're going to explore whether, for example, a K-class star, could that have a habitable planet or not? Perhaps it can. It would just be a bit, sky be a different colour. It might be a bit hot or a bit cold. But what we've now done is we're now randomly assigning a spectral class to our random systems. So Zangor is going to have a particular class of star, and the first thing they do is just have a colour based on the star spectral classification. So instead of doing system color like this, we're now going to say it's a property, and let's just do something dead simple. So if this dot spectral class is O, I don't think you can't switch on strings in JavaScript, can you? What we could do is, instead of this, right, okay. What we could do is this. Oops, no, that's not right. Let's just go back. Start again. Make sure we do this right. So this becomes 0, B becomes 1, A becomes 2, F becomes 3, G becomes 4, K becomes 5, and that's 6. Okay, so now spectral class is a number. So now we can do switch this dot spectral class. So if we wanted to print whether it's G, we'd have to look it up, but let's return white. I don't know if you can you use those? I'm not sure. Right, so let's just have a look back at this table. Actually these are blue stars, so O stars are blue. I don't really know what the CSS colours are, but these are blue-white, so they'd be light blue. A stars are white. I have no idea if this is going to work, because I don't know if this is even CSS classes. Case 5, orange. Case 6, so those are, let's just go with red. And the default purple. Right, so that should never happen. So it's just there as a kind of, if all goes wrong. Okay, so now, okay, so, oh, hello, we got a blue star. So if we go look at the things here, we should have an O. Yeah, we got one. We got one. Yeah, gateway is gateway was G. G was oh shit. So G is going to be 0, 1, 2, 3, 4. So gateway now needs to be spectral class 4. Okay, so now we've got a bunch of sort of kind of hand wavy accurate star classes. So our sector is now composed of stars which are actually gateway's white. Wasn't gateway should be a yellow star, right? Maybe I got the spectral class wrong. O is 0, B is 1, A is 2, F is 3, G is 4. We made gateway spectral class 4. Okay, not quite sure why. Maybe I got the colour for 4 wrong. 4 is yellow. That's puzzling. Let's just look at SY gateway spectral class is 4. Colour FE. Well, that what? Oh, bloody hell. Right. Override. Gateway is a yellow star. Okay, beautiful. Right, so we are now generating our sector. So we've gone from a mass of stars with random colours to now having Well, you can see here, this is one that's right on the edge, so we need to fix that up, but it's not a problem for now. It's a display problem more than anything else. But now what we have is a nice distribution of stars with some stars in the outer rim, and with a semi-realistic distribution of spectral classes, giving us white stars, blue stars, yellow stars, orange stars. I'm quite happy with how that's come out, so I'm going to end that session there. If you watched along, I hope you found this enjoyable.